Here in Washington, we have our own volcano threat in the Cascade Mountains, which on average erupts once or twice every century.
The threat includes Mount Rainier, which scientists continually monitor for activity. New at 6, KOMO meteorologist George Waldenberger spoke with a geophysicist about what she's been observing and what the risks are when it does eventually erupt.
Deep beneath the majestic forested terrain of the Pacific Northwest lies a hidden force of immense power, largely silent for centuries but never truly dormant. In recent months, a shocking scientific revelation has catapulted this underground phenomenon into the global spotlight, leaving geologists and volcanologists deeply unsettled. A research team utilizing the latest in subterranean imaging and seismic data has uncovered something chilling beneath the surface of Washington state. A massive interconnected magma corridor stretching farther and deeper than previously believed. What was once assumed to be a localized volcanic plumbing system centered around Mount St. Helens and its volcanic neighbors has now been redefined as part of an enormous underground structure, more vast, more active, and potentially more dangerous than anyone had predicted. Before we start, hit the like and subscribe buttons for more exclusive news. This magma corridor is not just a random series of molten rock chambers. It's a vast geological artery that links several of the region's most volatile volcanoes. Mount St. Helens, Mount Adams, and even the long-dormant Mount Rainier are now believed to be connected by this shared system of molten channels. High-resolution tomography scans and seismic wave tracking have mapped a corridor stretching over 100 miles in length and plunging miles into the Earth's crust, carrying with it a continuous flow of magma and volatile gases. The discovery has led scientists to reassess their understanding of the region's volcanic dynamics. No longer can each volcano be studied in isolation. They now represent nodes within a much larger and more complex geological network. The implications of this finding are enormous and deeply disturbing. For decades, scientists believed that the risk of volcanic eruptions in the Cascades was limited to the activity of individual volcanoes, with eruption events considered relatively isolated and predictable based on each mountain's unique behavior. That view is now obsolete. The shared magma corridor suggests a level of systemic connectivity between volcanoes that could lead to cascading eruptions, where pressure or movement in one part of the corridor might set off activity elsewhere. An eruption at one volcano may no longer be a singular event. It could potentially destabilize magma chambers tens of miles away, creating a domino effect that results in multiple simultaneous or sequential eruptions. Adding to the concern is the fact that this magma corridor appears to be more active than previously thought. Seismic tremors, many of them too small to be felt at the surface but clearly detected by instruments, have been increasing in both frequency and depth along the corridor. These quakes are indicative of magma movement and pressure buildup deep underground. The presence of long-period earthquakes, often associated with the fracturing of rock due to the slow influx of magma, has alarmed experts. These seismic patterns are not random. They suggest a dynamic and evolving system that is preparing for a release of energy on a scale not seen in modern history. Thermal imaging has further intensified the concern. Heat signatures emanating from deep beneath the Earth's surface show zones of elevated temperature consistent with large bodies of magma, some of which are closer to the surface than previously detected. These hotspots are not stationary. They are migrating slowly, sometimes appearing beneath regions not previously considered high risk. This has led to the reevaluation of hazard maps for the entire Pacific Northwest. Cities and towns that once believed themselves safe due to their distance from well-known volcanoes are now being reconsidered as potentially vulnerable due to their position relative to the expanding corridor. Even more disturbing is the corridor's orientation. Rather than running in a straight line along the Cascade Range, it twists and turns through the crust, branching off in unexpected directions and sometimes dipping toward densely populated areas. There is mounting concern that magma could find a new pathway to the surface in places that lack any historical precedent for volcanic activity. Such a development would mean an eruption in an area completely unprepared, lacking the infrastructure, monitoring equipment, or emergency response plans necessary to cope with such an event. Scientists are also grappling with the question of what this corridor means for the pressure dynamics between the connected volcanoes. When magma moves through this shared system, it doesn't simply build pressure at one point, it redistributes stress throughout the corridor. This redistribution can have destabilizing effects. A minor eruption or even a gas release at one point could cause subsurface shifts that destabilize another chamber miles away. In essence, the corridor acts like a massive underground pressure valve. Only instead of diffusing energy, it may transmit it dangerously across great distances. One of the most worrying aspects of the corridor is the potential for magmatic eruptions, in which magma interacts violently with groundwater. The corridor's trajectory brings it near several large aquifers and subterranean water reserves. If rising magma comes into contact with these water sources, the result could be sudden explosive eruptions that eject ash, steam, and volcanic rock at extreme velocities. These types of eruptions can occur with little warning and are notoriously difficult to predict. They also tend to produce fine ash that can travel hundreds of miles, clogging airways, contaminating water supplies, and crippling infrastructure. The corridor also raises concerns about the accumulation of volcanic gases, especially carbon dioxide and sulfur dioxide, which can build up in underground pockets and then suddenly escape. These silent killers are colorless and odorless, and they have been responsible for deadly incidents around the world when they have erupted from the ground without warning. The Magma Corridor acts as a conduit for these gases, and with its reach expanding into more populated areas, the risks of gas-related incidents are now part of the growing list of threats. Mount Rainier, in particular, has taken on new urgency in this revised understanding of the region's geology. Long considered one of the most dangerous volcanoes in North America due to its massive glacial cap and proximity to the Seattle-Tacoma metropolitan area, Rainier's connection to the corridor implies it could be activated or destabilized by events occurring miles away. The danger is not limited to a full-scale eruption. Even moderate volcanic activity could trigger massive lahars, volcanic mudflows that rush down the mountain's flanks, devastating valleys and towns in their path. These flows can travel at highway speeds, obliterating everything in their way with little or no time for warning. While there is no indication that an eruption is imminent, the scale and interconnectedness of the corridor mean that the warning time for future eruptions could be significantly shorter than previously estimated. Traditional indicators such as ground swelling, localized earthquakes, or gas emissions may not precede an eruption in the expected manner if the pressure is transferred or relieved in one part of the corridor and then suddenly shifted to another. This unpredictability is what truly horrifies experts. It undermines the reliability of existing monitoring systems and creates a landscape where prediction becomes guesswork rather than science. The broader implications extend beyond the Pacific Northwest. The discovery of such a large and active magma corridor challenges assumptions about volcanic systems globally. If such a hidden corridor can exist beneath a heavily studied region like Washington, how many other similar systems might be lurking unnoticed beneath other volcanic ranges around the world? It has forced a reckoning within the geoscience community about the limits of current technology and the need for more aggressive and widespread subterranean mapping initiatives. Economically, the revelation could have profound impacts. Insurance models, infrastructure development, and disaster preparedness plans are all built on historical data and presumed risk zones. The corridor invalidates much of that data. Areas once considered low risk now face uncertainty, while those in moderate risk zones may be significantly more vulnerable than previously thought. This could influence everything from housing prices to federal disaster response funding and emergency evacuation protocols. Large swaths of Washington and even parts of Oregon and Northern California may need to be reclassified in terms of volcanic hazard. For indigenous communities and long-established towns that have coexisted with the mountains for centuries, the news strikes a deeply emotional chord. These landscapes are more than just geological features. They are cultural landmarks and spiritual centers. To now face the prospect that these same mountains may be part of a coordinated system capable of unleashing destruction across hundreds of miles is a psychological blow as well as a practical one. It challenges the narratives of familiarity and safety that people have built around these places. Adding another layer of complexity is the impact of climate change. As temperatures rise, glaciers that cap these volcanoes are melting at accelerated rates. This not only increases the risk of lahars, but also potentially alters the pressure dynamics within the volcanoes themselves. Less ice means less weight pressing down on magma chambers, which can, in theory, facilitate easier magma ascent. Combined with the interconnected corridor, these changes could accelerate the timeline for potential eruptions or alter their expected intensity. The scientific community is racing to install more sensors, expand real-time monitoring systems, and develop models that can incorporate the complexities introduced by the corridor. But the sense of urgency is palpable. It's not just about more data. It's about decoding a vast, dynamic system that has only just revealed itself in full. The corridor is like a sleeping beast with its limbs stretched across the landscape, and for the first time its breathing can be heard beneath the earth. The question is not whether it will wake, but when and how violently. This discovery has ignited a surge of collaborative efforts among geologists, seismologists, atmospheric scientists, and emergency planners. Multidisciplinary teams are now trying to model worst-case scenarios, taking into account simultaneous eruptions, massive ash plumes, pyroclastic flows, and secondary disasters like landslides, tsunamis in nearby coastal areas, and extended power outages. The potential for regional paralysis is real. Transportation corridors, including I-5 and major rail lines, run dangerously close to many of the fault lines and volcanoes now implicated by the corridor. In a high-magnitude eruption scenario, the region could be cut off with limited ability to move people or resources in or out. While the initial discovery of Washington's massive Magma Corridor sent shockwaves through the scientific community, the unfolding picture has become even more intense as researchers delve deeper into the corridor's internal composition, behavior, and geological timeline. This is not just a molten pipeline waiting to erupt. It is a dynamic and evolving structure, exhibiting signs of intelligent geological architecture. Within this seething underground labyrinth lie zones of varying pressure, heat, viscosity, and even chemical makeup. These variations matter because they shape how magma flows, where it collects, and how violently it might one day reach the surface. Chemical analysis of magma samples from different parts of the corridor has shown that this is not a homogeneous system. Rather than being filled with uniform basaltic or andesitic magma, the corridor contains patches of distinct magma types, each with its own eruptive personality. Some sections harbor silica-rich magma, which is far more viscous and explosive. This type of magma doesn't flow easily. It traps gas until the pressure becomes catastrophic. These pockets act like underground bombs, primed to detonate when triggered by tectonic shifts or the arrival of fresh magma from below. The complexity of this corridor reveals a horrifying reality. It is not just a geological structure, but a reactive one. Different parts of the corridor could respond differently to the same stimulus. A deep tremor in one section might simply dissipate in an area with fluid basalt, but ignite a pressure crisis in a silica-heavy zone. This means that forecasting an eruption or collapse becomes infinitely more complicated. It's like trying to predict the behavior of an animal that changes its nature from moment to moment. Another revelation came when scientists discovered signs of magma fingering, narrow conduits of magma that snake out from the main corridor and rise independently toward the surface. These thin, almost invisible channels are particularly dangerous because they can serve as early paths for magma to rise in places where no historical volcanic activity has occurred. They are stealthy, forming over time, often without producing noticeable seismic activity until magma is already close to the surface. This discovery broadens the area of concern far beyond the immediate shadow of existing volcanoes. What makes this even more unsettling is that some of these magma fingers are heading toward locations that have not been geologically studied in depth due to their lack of volcanic history. Urban centers, industrial zones, and critical infrastructure such as dams and nuclear facilities are now being examined for their proximity to these newly identified subterranean paths. In some scenarios modeled by geophysical simulations, magma could reach areas like the Columbia River Basin, a region vital for agriculture, hydroelectric power, and regional transportation, causing devastating ecological and economic disruption even before a full eruption occurs. As more satellite and airborne geophysical surveys are conducted, researchers have identified subtle land deformations across a wider region. These deformations, slight uplifts and sinkholes, are often imperceptible to the human eye, but are clear indicators of subsurface magma movement. In several zones along the corridor, the ground has been rising steadily over the past decade, a sign that magma is pushing its way upward, applying pressure on the crust above. In other locations, Sudden subsidence suggests areas where magma may have drained away, leaving voids that threaten collapse or triggering localized seismic events. New models now suggest the corridor may have been active for far longer than previously assumed. Core samples from volcanic rock layers suggest that there have been interconnected eruptive events in the region dating back thousands of years, spaced across volcanoes miles apart, with chemical signatures indicating a shared magma source. This challenges the long-held belief that past eruptions were independent and isolated. It now appears that the corridor has been orchestrating regional volcanic activity for millennia, lying largely undetected while subtly reshaping the geological destiny of the Pacific Northwest. Perhaps the most haunting aspect of this finding is the realization that the corridor may be gradually becoming more efficient. Geological systems are not conscious, but they evolve. As magma repeatedly moves through the corridor, it melts and softens rock, carving smoother and faster paths over time. Just as water can carve a canyon over centuries, magma can open direct, low-resistance highways through the crust, allowing for quicker pressure release and more rapid ascent. In short, the corridor is self-improving, its own terrifying architect of future catastrophe. It also appears to be capable of recharging itself. Deep mantle imaging has revealed a vast plume of magma beneath the corridor's southern end, continuously feeding the system like a fire hose of molten rock. This plume is extraordinarily hot, rich in volatile compounds, and rising slowly from deep within Earth's mantle. As it fuels the corridor, it not only sustains its activity, but may also be gradually enlarging it. The Magma Corridor is not a fixed tunnel. It is expanding, branching, and evolving. Over time, it could grow into a structure rivaling those found beneath supervolcanoes. That leads to the next terrifying possibility. Is this corridor the precursor to a supervolcanic complex? The sheer size, energy, and complexity of the corridor has led some experts to draw comparisons to systems like Yellowstone's caldera or Toba in Indonesia. While Washington's corridor has not yet exhibited signs of forming a caldera itself, it possesses many of the hallmarks of a system in early development: massive magma reservoirs, deep volatile rich plumes, seismic swarms, long-distance fluid mobility. If a large enough portion of the corridor were to become destabilized at once, the result might not be a single eruption, but a massive region-wide geologic upheaval with global consequences. While a supervolcanic eruption may still be a distant possibility, a more immediate concern lies in how the corridor is affecting the water cycle and atmosphere in the region. As magma rises, it heats underground aquifers, altering the chemistry of natural springs, rivers, and soil. In some areas, acidic gases like hydrogen sulfide have started to appear in water samples, corroding pipes and posing health risks to rural communities. Soil near the corridor has shown signs of unusual warming, affecting agriculture and even altering local ecosystems as heat-tolerant species begin replacing native ones. The corridor has also started to influence weather patterns subtly. Volcanologists and meteorologists have noticed that in areas of elevated geothermal activity, the release of water vapor and gases is creating localized microclimates. These zones can trap heat or alter wind patterns, particularly in valleys and river basins. While the effects are not yet large enough to be considered climatic events, they are noticeable enough to register on atmospheric sensors. A sufficiently large release of volcanic gases, particularly sulfur dioxide, could cause acid rain or reflect sunlight, triggering temporary regional cooling. Strategic planners and military analysts are also beginning to pay attention. The corridor poses a risk not just to civilians but to national security infrastructure. Major military installations, communication hubs, and transportation routes run through areas now identified as being at increased risk due to magma migration. The potential for sudden disruptions, even from minor eruptions or subsurface gas releases, has prompted discrete risk assessments. In some scenarios, a volcanic event could cut off Pacific ports or disrupt key supply chains, with national and even global ramifications. There is also a psychological toll. As this revelation becomes more widely known, communities are grappling with fear, uncertainty, and a growing distrust of prior assurances of safety. For decades, volcanic risks in the Pacific Northwest were downplayed due to long intervals between major eruptions. The corridor undermines that sense of security. People now face a reality where the danger isn't a distant mountain, but the ground beneath their own feet. It's a quiet menace, hidden from view but steadily pulsing, shifting, and growing. Despite the best efforts of scientists and policymakers, there remains a significant gap in communication and public preparedness. Unlike earthquake risks, which have been widely publicized and incorporated into school drills and building codes, the concept of multi-point volcanic risk from a subterranean corridor is new and difficult to convey. Public education campaigns are only just beginning to pivot, with emergency services struggling to craft strategies for a hazard that could manifest anywhere along a shifting 100-mile-long line. The unpredictability of the corridor also complicates engineering responses. Building lava-resistant structures or installing gas vents only makes sense when hazards are localized. But the corridor's reach means that no single solution will work for every region. Some towns may need evacuation plans, others may require new infrastructure designs, still others may need early warning systems akin to those used in Japan or Iceland. Each solution is costly, and the sheer scale of the corridor makes comprehensive protection nearly impossible. If you liked this video, please give it a like and subscribe to our channel. Also, could you leave your comments below and tell us? What are your thoughts on Washington's Magma Corridor? Could a major eruption be coming? We want to hear from you. Thank you for watching and see you next time.